Hi everyone, welcome back again to Mathematics for Engineering 3 International Program, เกษตรศาสตร์ University. It's me again, M. Today we're going to be talking about first order homogeneous systems, and this is the second video of this chapter. The first video is about the introduction, okay, and for the second section there are going to be 4 videos. The first video is going to be this one, okay, for the second section, and it is the case where the roots are distinct, okay, and the second video will be the case where the roots are repeated, part 1, okay, and the third video is going to be part 2 of the repeated roots, and of course the fourth video will be the case where the roots are complex numbers, okay, and we'll get into that. But in this video it's going to be the first case where the roots are all distinct. Okay, so let's start here. First, let me talk a bit about the first order homogeneous systems. I told you guys before, right, in the introduction video, that this is the metric form a prime x equals ax. Okay, and if you notice, our b right now is 0. Okay, and that is the meaning of homogeneous, right? It's homogeneous even only if the matrix B is the zero matrix, right? It's a vector, it's a zero vector. And if we start with the x prime equals ax, then if I just, move this guy to this side, we would have that ax minus a prime equals 0. Okay, and if we assume that the root is in some form, for example, if we assume that x is a vector, don't forget x here is x1 x2 to xn. Okay, if you assume that x is some vector k times e to the mt. Okay, we did pretty much the same thing before in chapter 2. If you remember, we assume that y is c1 e to the mt, if you remember. Okay, so we did, we are doing pretty much the same thing, but in the metric sense. Okay, so x is the matrix and k is the matrix as well, and e to the mt. Okay, we just assume that x takes this form where k is a vector of constants. Okay, so k is a vector of constant and m is just a constant. Okay, we don't know much, we just assume this. Okay, we just assume this. First, we know that x prime would be, what is it? M is a constant, k is a constant, isn't it? So we have m, okay, we have k, and we need to differentiate e to the mt. So we get e to the mt, and then we have m here, right? That is to differentiate e to the mt when m is a constant. Okay, don't forget guys, we differentiate by t, which is the independent variable. Okay, so we have ax minus x prime equals, what is it? What is ax minus x prime? Ax would be a k e to the mt. Don't forget guys, we now assume that x equals k e to the mt. Okay, that's ax minus x prime, and x prime is m k e to the mt. Okay, and then I pull k e to the mt out, so I get a minus mi and k e to the mt. Okay, guys, don't forget, if we pull these guys out, so we get this term, But m is just a constant. M is just a constant. It's a number. It's like 1, 2, 3, 4, 5. It's a number. But A here is a matrix. So, from high school, you remember that if we pull the matrix from the constant, you need to get the matrix I. For those who don't remember, the matrix I is the identity matrix. Okay, which means that it's all 1 in the diagonal line and the rest are 0. Okay, and because ax minus k ax minus x prime is 0 from here, so we have that here is 0. Good, because ax minus x prime is 0. Okay, then guys, e to the mt is exponential, right? Exponential. So e to the mt can't be 0. Okay, and if e to the mt can't be 0, it means that this guy is 0. Okay, and if this guy is 0, it means that from high school, it means that the determinant of a minus mi is 0. Okay, because we assume that k is not 0 as well. K is not 0 as well. So if k is not 0, this guy is going to be 0 when this determinant is 0. And we call this equation characteristic equation. Okay, we have this kind of equation before, the characteristic equation in chapter 2, but it's a little bit different from chapter 2. So you need to be able to remember this equation. You must remember, you must memorize this equation. The characteristic equation is the most important equation in this chapter. Okay, cool. So let's get to the first case, the distinct roots. Okay, the method. First, we need to solve the characteristic equation. Okay, we solve the characteristic equation for m. Okay, we solve the characteristic equation for m. And then we call the m's eigenvalues. Those are the m's, m1, m2, m3, m4 until mn. Those are eigenvalues. And if, in this case, they need to be distinct, which means that they are all different. Okay, all the m's are different. This is the first case. It's quite similar to chapter 2, right? When we were solving the higher order differential equations. And then we need to find eigenvectors. Okay, we have two new terms. The first term is eigenvalues. Eigenvalues are the m, which satisfy this characteristic equation. Okay, and when they are all distinct, we then find the eigenvectors, which are the vector case. Okay, the vector case. So these vector cases are called eigenvectors. Okay, how to find eigenvectors? We find it from this equation. And this equation is nothing, it's from here. Okay, a minus mi times k equals 0. Okay, so we can find the eigenvector from here. So for each m, For example, for M1, you get K1, and that is the eigenvector corresponding to the eigenvalue M1. And for M2, you get K2, and similarly, for Mn, you get Kn. So once you find the eigenvectors, it will become clearer when you look at the exercises, okay, the examples. But right now, just just accept it, okay, just accept the method, okay. And once you get the eigenvectors, the solutions are x1 equals k1 e to the m1t, which is the one that we assumed. Okay, x equals k e to the mt. So the first solution, x1, is going to be k1 e to the m1t. And similarly, x2 is k2 e to the m2t, and so on. So we get xn equal kn e to the mnt. And the general solution is just the combination of each solution. Okay, so basically we can say that x, which is the solution, is c1 x1 plus c2 x2 plus c3 x3 plus blah 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 plus cn xn. But the x1 is this guy, okay, and x2 is this guy, and so on. Okay, so let me sum it up. First, we look at the characteristic equation, the most important equation in this chapter. Second, we look at the eigenvalues, m1, m2, m3 until mn, and they need to be all distinct. Okay, this is the first case when they are all different. And then we find the corresponding k1, k2 until kn by using this equation. Okay, how? We'll see. And once we get k1, k2, k3, k4 until kn, we get x1, which is k1 e to the m1t, x2, k2 e to the m2t, x3, k3 e to the m3t, and blah blah blah. And then the solution is c1 x1 plus c2 x2 plus c3 x3 plus blah blah blah. In other words, it's c1 k1 e to the m1t plus c2 k2 e to the m2t plus blah blah blah. Okay, and this is the case when all the roots are distinct. Okay, so let's look at some examples. First example. So to find the general solution for these two equations, first we need to write them down in terms of metrics, right? We need to write in metrics form. And if you notice, the metric form is, so I'll call this x prime, okay? And this is y prime. So the matrix form would be x equals a x when, okay, let's write it down like this. It's going to be x prime y prime equals 2 3 no 2 1 3 4 and then xy, right? Because if you multiply this matrix, you will get x prime equals 2x plus y, and you will get y prime equals 3x plus 4y, and that is the matrix form. Okay, and if you notice, here is just x prime equals ax, and you can see that it's actually plus b and plus b here, but b here is 0, which means that it is the homogeneous system. Okay, so let me put it here. So that is the matrix form. Okay, so to solve it, let's get back to the method. First, we need to solve the characteristic equation. So the characteristic equation is uh, determinant of a minus mi equals 0. Okay, and guys, don't forget I is the identity matrix. A right now is 2 times 2, right? The dimension of A is 2 times 2. So I would be 1 0 0 1, right? Right? So Mi would be M0 0 M. Okay, so that would be determinant of A, which is 2 1 3 4 minus M10 0 1 equals 0, and that is determinant of 2 minus M 1 3 and 4 minus M equals 0. Or you can write it down this way, which is this stands for determinant. Okay, the one without this, that is determinant, and there will be 2 minus M 1 3 4 minus M equals 0. Guys, I am doing it really slowly, but in the exam you don't need to do all of this. Okay, you just take A, which is this guy, and then you minus M to the diagonal line, okay, which is this line. Okay, so you get 2 minus M 1 3 and 4 minus M. Let me make it a little smaller and use the red color. So you just need to minus M. I'll jot it down here for you. So we just need to minus M to the diagonal line, which is this line. Okay, so just need to take A which is 2 1 3 4, and then you minus M to the diagonal line. Good. And then you need to find this determinant, which is, what is it? Determinant of this. You know how to find determinant, right? If you multiply down, okay, you get plus. You multiply up, you need to put minus. Okay, that's the way to find the determinant. So here, this times this, you get 2 minus M times 4 minus M. And then you multiply up, so you get 3. But to multiply up, you need to put minus. Okay, so you get minus here equals 0. Okay, to find the determinant, for those who don't remember how to do so, you multiply down, okay, and then you multiply up. But when you multiply up, you need minus sign. You need the minus sign, which is this guy. Okay, and then I solve this. I get 8 minus 2M minus 4M plus M squared minus 3 equals 0. And that is M squared minus 6M plus 5 equals 0. And then I factorize it. I get M 5 1, and then I get minus, which means that let me put it up there, which means that my M is 1 and 5. Okay, and these M's are called eigenvalues. Okay, so right now we are here, right? We solve the characteristic equation, we get the eigenvalues, and as you can see, they are all distinct, right? You get 1, and then you get 5, which are different. Okay, so if I say that M1, I'll just use the green color. M1 is 1, Okay, so I want to find k, the eigenvector, right? We want to find, okay, don't use WTF. Let's say we want to find k1. Okay, and we can find k1 using this equation. So we have a, which is 2 minus m minus 1, 1, 3, 4, 4 minus 1, and then we have k1. Okay, let's say if I assume that k1 is k1 and k2, like that. Okay, this is a big k though, this is a big k, this is a little k, it's a little k. So it's going to be multiply k1 k2 and then equals 0. Guys, don't forget here, it's a minus m1 times k1 equals 0. But it's m1i, right? Which means that you need to subtract the m from the diagonal line, which is 2 minus 1, 4 minus 1, right? This is the m, this is the m1. Okay, and you subtract it from the diagonal line. Okay, and so we have that is 1, 1, 3, 3, k1, k2 equals 0, which means that I multiply this to this, so I get the k1 plus k2 equals 0, and 3k1 plus 3k2 equals 0. Okay, and as you can see, these two equations, they are the same, right? Because if I divide this equation by 3, I will get k1 plus k2 equals 0 as well. Okay, so these two equations, they are the same. In that case, we have that k1 is minus k2. Okay, okay, so our big vector k1 would be k1, k1 is minus k2, right? K1 is minus k2. So we have minus k2 k1, minus k2 k2, right? Because k is k1, but k1 is minus k2. So we have it here, minus k2 and k2. And then once we are here, we can substitute the value of k2 with some number. Usually we just let k2 be 1. Okay, but in reality, you can, choose k to be 5, 10, 1000, minus 1, any numbers you like. Okay, but not 0, because if k2 is 0, this guy is going to be 0. Okay, and k will be the 0 vector. Okay, so we can pick any value k2 except 0. So usually we just pick 1 because that is easy. So we have here minus 1 and 1. Okay, and our solution x1 is k1 e to the m1t. Okay, which means that one second, which means that x1 is k1, which is minus 1 and 1, e to the m1, which is 1 is m is 1 is 1, right? Which is e to the 1t. Okay, so right now we obtain the first solution x1. Okay, let me do it again. Let me run through this again. First, we look at the characteristic equation. We solve the characteristic equation, right? Which is 2 minus m to the diagonal line, this line, from A, okay, from this A. And then you let it be 0. Then you solve for m, you get 1 and 5. And first, we look at the first m, m1 equals 1. Then we need to find the eigenvector, right? If you go back here, right, we get m1, we need to find k1, okay, from using this equation. So using this equation, which is this one, right, a minus mi k equals 0, right, which is this equation. And then we get this relationship of k's, okay, and we have that k1 is minus k2. So the vector k1 is going to be minus k2 and k2. In that case, we can substitute k2 with some number. In this case, I pick 1. So I have minus 1 and 1. Okay, so I have minus 1 and 1. So our first solution is x1 is k1e to the m1t. So we have x1 is k1e to the m1t. So x1 would be k1, which is this guy, and e to the m1t, or minus 1 and 1 e to the t. And that is the first solution. Okay, after that, we need to use m2 equals 5, right? And then we need to get k2, and then we get x2. Okay, so we take m2 equals 5. So in that case, we need to find k2, which let's say k1, k2. Okay, and then we can find that using this equation, right? So it must be a minus m1i k, oh sorry, m2i k2. Okay, so in that case, we have that a, which is 2 minus 5, 1, 3, 4 minus 5. And then we have k1, k2, and then we have 0. Okay, this is from the equation a minus m2i k2 equals 0. Okay, because I is the identity matrix, right? So we subtract it from the diagonal line. Okay, so here we would have that it is what is it, minus 3, 1, 3 minus 1, and we have k1, k2 equals 0. And this means that minus 3k1 plus k2 is 0, and 3k1 minus k2 is 0. And you can see that these two equations, they are the same. Why? Because if you multiply the second equation by minus 1, you would get minus 3k1 plus k2 equals 0, which is the same as the first equation. Okay, so it means that we have the same equation. Okay, so right now we know that k2, so we know that k2 is actually 3k1. Okay, k2 is actually 3k1. Okay, so the vector k would be k1 and 3k1. Okay, k1 and 3k1. So you can see the pattern. You need to write it down in terms of one variable, which is k1, or you can write down in terms of k2 as well if you want, but you know, k1 is a little easier. So you can substitute k1 with any number except 0. So I let k1 be 1. So this vector would be 1, 3. Okay, so we get vector k2, which is 1, 3. So our second solution x2 would be k2, which is k2, which is 1, 3 e to the 5t, right? Right, because x2 would be k2 e to the m2t. Okay, it means that our solution x is c1x1 plus c2x2. Okay, let me get rid of my video. Okay, so here we would have c2, x1 is here, the first solution, and that is minus 1 and 1 e to the t plus, oops, sorry, that is c1 plus c2, and that is 1, 3 e to the 5t, and that's it. That is the solution. Okay, that's it. So just to wrap it up, we begin with the characteristic equation, right? This characteristic equation, we solve for m, so we get two m's. We get m1 and m2. After that, for m1, we want to find k1, right? So once we get k1, the first solution x1 would be k1 e to the m1t, and that is the first solution. After that, we take m2, which is 5, and then we find k2, right? And we find k2, and we get that k2 is actually 1, 3. Okay, k2 is 1, 3. So x2 would be k2 e to the m2t, which is 1, 3 e to the 5t. And so this is the second solution. So the solution, the general solution would be c1x1 plus c2x2, which is c1 and this is x1, and c2, this is x2. Okay. Okay, next example. This one, we have 3 independent variables. Okay, so this one, I can write it down in terms of x prime is 0x plus 0y plus minus z, and y prime is 2x plus 0y plus 0z, and z prime is minus x plus 2y plus 4z. So if we want to write that down in the matrix form, it would be, what is it? X prime, y prime, z prime. Okay, and the matrix A would be 0, 0, minus 1, 2, 0, 0, minus 1, 2, 4. And we get x, y, z here. Okay, and because B is 0, which means that is homogeneous. Okay, so guys, if the question is already in the matrix form, that is good. But if it is in this form, you need to first change the form into the matrix form. Good. Good. Okay. After that, we want to find m's, right? We want to find the eigenvalues, okay, the roots. So we begin with this characteristic equation, which is a minus, sorry, determinant of a minus mi equals 0, which means that it is 0 minus m, 0 minus 1, 2, 0 minus m, 0 minus 1, 2, 4 minus m. Okay, basically we minus m to the diagonal line. Okay, okay, and we let this be 0. Okay, guys, do you remember how to do determinant of matrix 3 times 3? Do you? Okay, if you don't, I'll explain a bit. So here we get minus m, 0, minus 1, 2, minus m, 0, minus 1, 2, and 4 minus m. So to find the determinant, we just need to copy and paste the first two columns, right? So we would have here, we copy minus m to 1 here and 0 minus m and 2 here. Okay, and that is the first two columns. After that, we multiply down and multiply up. Okay, whenever we multiply up, we need to get the minus sign. Okay, I hope you do remember how to do so. Okay, so here, this determinant equals 0. Okay, so the first one we would have, what is it, minus m times minus m times 4 minus m, which is this one, and then we get 0, and then we get minus 1 times 2 times 2. Okay, after that we multiply up, so we need to get minus, and then it is minus 1 minus m minus 1, and then minus 0, and then minus 0 again, right? Because here you come across 0, as well, so those are 0, and this equals to 0. So here we have m squared, 4 minus m, minus 4. Here it's plus m equals 0, right? And then here we have m squared, 4 minus m. Here I pull minus 1 out, so I get 4 minus m equals 0. After that, I pull this 4 minus m out, so I get 4 minus m squared minus 1 equals 0, which means that 4 minus m plus 1, m minus 1 equal 0. Right here, we use a squared minus b squared. Okay, this is a, this is b. A squared minus b squared is a plus b times a minus b. So here we have that m is, what is it? What is m? So the m would be m1, m2, m3 would be minus 1, 1, and 4. Okay, the order is from smallest to biggest, right? Because m plus 1 equals 0, which means that m is minus 1. We did that before. Okay, so we have 3 m's, we have 3 eigenvalues. So next we need to find k1, k2, K3, right? We need to find K1, K2, K3. K1, the big K, K1, K2, K3. After that, we would get X1, X2, and X3. And the general solution X would be C1x1 plus C2x2 plus C3x3. Okay. 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 Let's continue. So first, let's take M1 equals minus 1. Okay. If M1 equals minus 1. So we let K be K1, K2. Okay, right now it's three-dimensional, right? So it need to be K1, K2, K3. Okay, right now because we have 3x, right? We have x, y, and z. So K need to be K1, K2, and K3. So uh, the equation that we use to find K is, if you go back to the method, we need to use this equation, right? A minus m1i ki equals 0. So here it would be A. What is A, guys? A would be 0, 0 minus 1 to 0, 0 minus 1 to 4, right? So we would have 0 minus 1, 0 minus minus 1, 0 minus 1, 2, 0 minus minus 1, 0, and then minus 1, 2, 4 minus minus 1. And then we have K1, K2, K3 equals 0. Okay? This is nothing. This is from A minus M1I K1 equals 0. Okay? And this is M1. Good. So here we have it is 1, 0 minus 1, 2, 1, 0 minus 1, 2, 5, and then we get K1, K2, K3 equals 0. Okay? Okay? And then we will write all the K, K2 and K3 in terms of K1. Okay? We write K2, K3 in terms of K1. So we have the equation, the system of equation. So we have K1, let me use another color. K1 minus K3 is 0. It's from here. It's from this times this. So we get K1, and then we get 0 K2, which is disappeared, and then we get minus K3. Right? We multiply matrix, basically. So we get 2K1 plus K2 equals 0. And minus K1 plus 2K2 plus 5K3 equals 0. Okay? Okay. So right now we have that K3 is the same as K1. Okay? And K2 is minus 2K1. Right? So you can write K as K1 minus 2K1 and then K1 again, right? Because K2 is minus 2K1 and K3 is K1. And then you can just substitute K1 with 1. So right now you have K1 is, here's K1 by the way. K1 is 1 minus 2 and 1, which means that you have x1 as k1, which is 1 minus 2 and 1, e to the m1, which is minus 1 t, and that is x1. Okay, it's gonna be very long, okay, because it's three-dimensional, right? But the method is the same. You just first you convert it into the matrix form. You get the matrix A here, right? This one is the matrix A. After that, you find M, right? By using this characteristic equation, right? So you get three M's, M1, M2, and M3, minus 1, 1, and 4. After that, if M is minus 1, we use this equation, right, to find k1, and then we arrive with this system of linear equations in k1, k2, and k3. So we write k2 and k3 in terms of k1, so we have the big k1 like that, and then we can substitute the little k with 1, so we get the big k1 like that. You could substitute k1 with 2 if you want. You can, it's up to you, but better to use k1 because it's easiest to use k1. And then the first solution x1 would be k1 e to the m1t, and that is the first solution. After that, you need to work for the second solution, okay? And you know that m2, okay, let me get the new page, and you know that m2 is 1, okay? We have minus 1, 1, and 4, right? So m2 is 1, okay? And we have that k2 is k1, k2, k3 again, okay? And from the equation, we have that a, what is a? Let me use the green color. A is 0, 0, minus 1. So we have 0, minus 1, 0, minus 1. And then 2 is here, A is here. Okay, 2, 0, 0. So we have 2 minus 1, 0. Okay, it's actually 2, 0, minus 1, 0. And the last line would be minus 1, 2, 4. So we get minus 1, 2, and 4, minus 1. And then we get k1, k2, k3 equals 0. Okay, and that is for m2, to find k2 in order to get x2. See, it's pretty simple, right? You get the eigenvalues m1, m2, m3, and then you find the eigenvector k1, k2, k3, and then you find x1, x2, x3. Okay, so right now here it would be minus 1, 0, minus 1, 2, minus 1, 0, minus 1, 2, 3, and you get k1, k2, k3 equals 0. Then you get the system of linear equation, right? So you get minus k1 minus k3 equals 0. It's from this row times this column. Okay, so you get minus k1, 0 k2, and then minus k3. After that, you get a 2k1 minus k2 equals 0, and then you get minus k1 plus 2k2 plus 3k3 equals 0. Okay, and then you write k2 and k3 in terms of k1 again. Okay, which means that k3 is minus k1, and here k2 is 2k1. So you have the k2 is actually k1 and 2k1 and then minus k1. After that, I substitute k1 with 1, of course. So what I have would be 1, 2, minus 1. And that is K2. Okay, in that case, I obtain x2, which is 1, 2, minus 1, e to the t, e to the 1t. And that is x2. And we need only one last x, right? Which is x3. And to find x3, we need to work with m3, which is 4, right? That's the third m. And oops, and that is 4. So in that case, I would write down K3 as the same, K2, K3, K1, K2, K3. So after that, I would have uh, 0 minus, it would be 0 minus 4, right? So I'm going to do it quickly, okay? I'm gonna do it quicker and quicker. But for the first two x's, I make it, really slowly so that you understand the process. But from now on, it's going to be, you know, somehow quicker. So it's going to be 0 minus 4, which is minus 4. 0 minus 1, and then 2, 0 minus 4, which is minus 4, 0, and then minus 1, 2, 4 minus 4, that is 0. And then you get K1, K2, K3 equals 0. Guys, this is the same thing. This is A minus M3, which is 4i, right? And then K3 equals 0. Okay, after that, you get the system of linear in case. So we have minus 4k1 minus k3, 2k1 equals 0, 2k1 minus 4k2 equals 0, and then we get minus k1 plus 2k2 equals 0. And then we write k3 as minus 4k1. And then K2 as 1 half K1. Okay, K2 as 1 half K1. So what we have next, we have that K3 would be, let's make it a little bigger. K3 would be K1, and then K2 is 1 half K1, and then minus 4 K1. Okay, you can let K1 be 1. You can, of course. But if you let K1 be 1, K3 would be 1, 1 half, and minus 4. And I don't like 1 half. Okay, I like integers. So I will let K1 be 2. I'll substitute K1 with 2. So in that case, this would become 2, 1, and minus 8. And that looks much better, right? So the third solution would be 2, 1, minus 8 e to the 4t. Okay, so once we obtain 3 solutions, the general solution x would be c1 x1 plus c2 x2 plus c3 x3 when the c's are constants. Okay, so we have here c1 x1 is 1 minus 1, 1 minus 2, 1 e to the minus t, and x2 would be plus c2 1 2 minus 1 e to the t plus c3 2 1 minus 8 e to the 4t, and that is the solution. Okay, it's not hard, is it? right? It just, you need to look at each term. Okay, so let me wrap it up. First, for this question, first you write it down in terms of matrix form. After that, you find eigenvalues m using the characteristic equation, right? Find the determinant of a minus mi, which is 2 minus m to the diagonal line. After that, for each m, you find the corresponding k, which is the eigenvector, right? By solving this equation, right? And then you write k2 and k3 in terms of k1, like that. So it's all k1. And then you substitute k1 with 1 or any other numbers that you like. Okay? And similarly, you get k2 and k3. Okay? In that case, when you get k1, k2, k3, you get the solution x as well. And the answer would be c1x1 plus c2x2 plus c3x3. Okay? And for this question, if we do have the condition that, the initial conditions that x0 is 3, y0 is 11, and z0 is 3. So in that case, we can compute, z1, c2, and c3, right? So from here, we obtain the the solution. Let me copy it here. Only this guy. And this is actually the x, right? So this is actually our x. But don't forget, our x is the vector of variables. So the x here is actually x, y, and z, right? So if you write it down in the regular form, you would have that x equals c1 e to the minus t plus c2 e to the t plus c3 2c3 e to the 4t. And similarly, you get y equals minus 2 c1 e to the minus t plus 2c2 e to the t and plus c3 e to the 4t. And z is e to the minus c1 e to the minus t plus minus c2 e to the t and plus c3, that is minus 8 c3 e to the 4t. Okay, this is the regular form of this. Okay, why? Because if you look at x, it's going to be c1 times 1 times e to the minus t, right, which is this guy. And if you want to find the second term, that will be c2 times 1 times e to the t, which is this guy. And similarly is 2c3 e to the 4t, which is this guy. So this is the regular form of the solution. Okay. Okay. In the exam, you don't need to write down the regular form. Okay, it's not necessary, but it's good to know how to write down the regular form. And next, if we want to find the constants c1, c2, c3, we just need to apply this condition. So up there we would have that x x0, right? It means that we substitute t with 0. So here x0 is 3, is c1 e to the minus 0 is going to be 1, right? Plus c2 plus 2c3. Okay, and that's the first equation when we substitute t with 0. And similarly here, when we substitute t with 0, we get 11 equals minus 2c1 plus 2c2 plus c3. And the last equation would be 3 equals c1 minus c2 minus 8 c3. Okay, and that is our uh, systems in C1, C2, and C3. And you have three equations, right? You have C1, C2, C3, three constants. So you can solve for C1, C2, and C3. I'm not going to show that, okay? I'm just going to give you the answer. And the answer is that C1 equals minus 2, and C2 equals 3, and C3 equals 1. Okay, and that is the answer. Okay, uh you can go and have a look at this. I'm not sure if these constants are computed correctly. Okay, if they aren't, you just compute it, because there's a typo in the book. Okay, but anyway, it's quite easy, right, to compute C1, C2, and C3. So the solution would be, assume that these C's are correct. Okay, assume that these C's are correct. The solution would be x equals minus 2 e to the minus t, and sorry, minus 2, 1 minus 2, 1 e to the minus t, plus 3, 1, 2 minus 1 e to the t, plus 1 to 1 minus 8 e to the 4t. Okay, just get rid of my picture. Okay, and that's it. Okay, that will be the particular solution. Okay, just in case they give you initial conditions, so you can solve for the particular solutions. Okay, okay, and that's it. Okay, guys, if these numbers are not correct, you know how to do it, right? Just solve for C1, C2, and C3, and then you put them here. That's it. Okay, and guys, that's it for the first case where uh, the eigenvalues. Right now, you know what eigenvalues are, right? When the eigenvalues are all distinct. Okay, when they are all distinct, we know that you can find the eigen vectors, the k1, k2, k3, right? Using the equation a minus mi, the big I, times k equals 0, right? And then you can solve for k, right? K1, K2, and K3. And to solve for k, you will obtain the systems of linear equation in K1, K2, K3, right? In this little k, right? And in that case, you just write K2 and K3 in terms of K1. Okay, and then you substitute K1 with some numbers. Let's say 1, easiest. Don't substitute it with 0, okay, because we don't want the vector big K to be 0. We don't want that. Okay, so just substitute it with 1. That's the easiest. Or if you have fractions, you have 1/2, you might want to substitute it with 2, so that you only have integers. Okay, but it's up to you. It's your choice. Okay, so once you get the case, you can get the x as well, the solution, right? Because x1 is just uh k1, right? E to the m1t, right? And then you obtain the general solution, which is the combination of the solutions, right? It's going to be c1 x1 plus c2 x2 plus c3 x3, and that's it for the first case when when the eigenvalues are distinct. In the next video, we're going to be looking at the second case when the eigenvalues are repeated. Okay, when they are repeated, they are not distinct. Okay, it's not m1 equals 1, m2 equals 2, m3 equals t. It's not like that. Maybe m1 is 1, m2 is 1 as well, and maybe m3 is also 1. And that is when eigenvalues are repeated. Okay, we're gonna see that in the next video. Guys, try to understand each case perfectly. Why? Because if you don't understand this case, you move to the next case, it's gonna be, it's gonna be confusing, right? Because you can't, distinguish, you can't differentiate between the two cases. So try to understand it case by case and try to understand it well. Okay, and you won't have any problems with this section. Okay, and this chapter as well. So see you in the next video, guys. Bye bye.